Logic gates. There are two main types of electronic circuits, devices or systems, analog and digital. In analog circuits, voltage and currents can have any value within a certain range over which they can be varied smoothly and continuously. In digital circuits, voltages have only one of two values, either high, 5 volts for example, or low, near 0 volts for example. Many electronic circuits have to make decisions. They look at two or more inputs and use these to determine the outputs from the circuit. The process of doing this uses electronic logic, which is based on digital switches called gates. Logic gates are the building blocks of a digital circuit, and they are switching circuits used in computers and other electronic systems. Logic gates allow an electronic system to make a decision based on a number of its inputs. There are 5 basic types, all made from transistors and integrated circuit form. The behavior of each is described by a truth table showing what the output is for all possible inputs. Each input and output of the gates must be one of two states. 1 represents the presence of an electrical voltage. It can be referred to on. 0 represents the absence of an electrical voltage. It can be referred to off. There are many types of logic gates, each with their own characteristics. The behavior of each is described by a truth table showing what the output is for all possible inputs. NOT gate or inverter. A NOT gate has just one input, and whatever the input, the gate inverts it. If 0 is input, then the output is 1. If 1 is input, then 0 is output. The truth table looks like this. AND gate. An AND gate can be used on a gate with two inputs and tells us that output is 1 if input A and input B are 1. The truth table looks like this. OR gate. The OR gate has two inputs. One or both inputs must be 1 to output 1. Otherwise, it outputs 0. The truth table looks like this. NOR gate. An OR gate can be used on a gate with two inputs. NOR tells us that output is 1 if neither input A nor input B is 1. The truth table looks like this. NAND gate. An AND gate can be used on a gate with two inputs. NAND tells us that output is 1 if input A and input B are not both 1. The truth table looks like this. Pay attention in the symbols. They are very important. Before continuing, let's remember that a truth table is a method for recording all the possible input combinations and determining the output for each. It's usual to use A, B, C for inputs and P, Q, R for outputs. Example. P equals A and B. In this example, A and B are inputs. P is output. Now draw a diagram to represent this expression. Complete the truth table for this gate. Don't forget that output P is 1 if input A and input B are 1. Example: P equals A or B. A and B are inputs. P is output. Draw a diagram to represent this expression and complete the truth table for this gate. Don't forget that output's 1 if either or both of the two inputs are 1. Some logic gates may have more than two inputs. Let's study some of them. P equals A and B or C. Draw the gate A and B. Now draw the gate or C. In this diagram, we have three inputs, A, B, and C, and one output, P. You should notice that the AND gate output will be one of the OR gate inputs. So let's name this output by D. D is not an input. It's an intermediate value which we will use when calculating the truth table. Since the circuit has three inputs, the truth table will have 8 rows. D is equal to A and B. If you note only columns A and B, you can easily fill out the D column in the table. You just put 1 everywhere that A and B are both 1, and 0 everywhere else. Notice that D doesn't depend on C in any way. P is equal to D or C, so we can now fill out the P column in the table, the actual output of the combination gate. We just put 1 everywhere that either D or C are 1, and 0 everywhere else. In this diagram, the not A output will be one of the OR inputs. The AND gate output will be one of the OR inputs. So let's name these outputs by D and E. Since the circuit has 3 inputs, the truth table will have 8 rows. D is equal to not A. This is the simplest gate. Whatever the input, the gate inverts it. E depends on B and C. To complete E column, we just put 1 everywhere that B and C are both 1, and 0 everywhere else. Now we put 1 everywhere that either D or E are 1, and 0 everywhere else.